This is properties of matter, first section, that is elasticity. First, I'll discuss about the theory, and after that, examples, later hard questions. Elasticity is very simple. Elasticity is very simple section. Here we discuss about the matters or the substance and how it behaves when forces are given. Normally, basically we can consider about metals. Directly when you consider metal, there should be a certain shape for that. Metal is extracted, you don't get a shape, but it goes with three different ways. One is linearly made ones. But not only metals, finally we discuss about the others also. So, right, that is also there. Then, first one we have to consider linearly. Then it's a wire or string. String also we can apply. String. Then, second one, you apply certain force on a certain area. Then we could consider that separately. That is not that much in new syllabus. Even for volume, it can be. A force can be applied to a certain volume of metal or any substance. Then volume of. But mainly we consider linear ones. Now, when there is a force, we'll say it's a wire, given on the other end, when it is suspended on the ceiling. Normally what happens is, it extends its length. It extends its length. This is the original one. This is the first diagram. Second diagram, I'll draw the same thing. On the same diagram, if I draw, it will be a problem. So therefore, I'll draw like that. Here the force is given. A force is given vertically down. A force is given vertically down, then it increases its length. It increases its length. So this is the increase in the length. That increase in the length is called extension. Extension. So then, this is what happens is when a force is given to the string vertically suspended one, it increases its length. But if you can make it horizontally keep and a force can be given, then same thing will happen. But easy purposes, we consider vertical strings. Now, this wire is concerned, it has a certain cross-sectional area that is denoted by area. It's a cross-sectional area denoted by normally A. Extension is denoted by simple E. The applied force is F. If you refer any book like that, some books without F, there is a mass suspended. Mass is suspended. So the force is then mg. So instead of this, they draw directly mg like that. That is also. But you can understand another one. When a force is given to a string, there is a tension, the wire gets. Normally, in mechanics, any point, any substance, or any object, not a substance, is in equilibrium. We'll say a point. There is a force downwards, that is F. Upward forces are there. Here in this case, we consider only this part. Then upward tension is there. Tension is T. So then this is in equilibrium now. It doesn't move now further. So that situation, it is this point or the object. If it is an object is in equilibrium. So therefore, we can resolve the forces vertically upwards. T minus F is equal to 0. That is mechanics. In mechanics, when an object is or any point is in equilibrium, when you resolve to any direction, the total value, the sum of the components and all the forces towards one particular direction is equal to 0. But most of the teachers and books, they say upward forces are equal to downward forces. That is not directly from the theory. Upward forces are equal to downward forces comes with this equation. Now, here we can consider then T is equal to F. Later for questions, we need that. Anyhow, I'm going to erase this part because it's mechanics part. We can apply later. This is extension. This is area. There is a force. And this has a original length or initial length. It is simple length. That is original length or especially we call it original length or initial length. Then we have to explain certain theories. First of all, write your notes quickly. Under this section, we study certain wires or blocks made of different material behave when a force is applied. Initially, we consider linearly. That means how it happens when a force is given to a wire or string suspended vertically. In this diagram, first you can see the diagram 1. There you get the initial situation of the wire. In the second one, then right, in the first diagram, it gives the initial situation. There are no forces applied. In the second situation, a force is applied. A force is applied. And the length of the wire or string increases. That increased length is called extension, denoted by simply some other mechanics sections, extension is denoted by simple X also. But here we consider first letter of the extension. Then the original length is considered as simple A. And the wire has cross-sectional area and it is denoted by capital A. The force given or exerted to the bottom of the wire vertically down, bottom of the wire vertically down is denoted by capital A. I have considered 4 physical quantities here. Now, you can understand this. When this is being extended, the wire, the amount of the volume of the material, especially volume, mass also same, remains constant. Therefore, when it is extended, when it is extended, area reduces. But there is another physical factor defined that is not in the syllabus now. That is called Poisson ratio. That is not there. But when you are doing the question, remember, we can consider volumes are equal. Density we can't say because we don't know that. If you consider density is the same, that also can be considered with mass. Right. Now, right, when the extension takes place, when the extension takes place, the volume of the wire does not change. It remains constant. Therefore, the cross-sectional area of the wire decreases since the length increases. Main reason is it increases, that happens. So the needful things you can draw. First situation, second situation. If you want to get to know about the theory of mechanics, there, those things you can note down now.
Okay, sir.
Now, I will explain another two main factors. First one, the normally you have done. So then stress is, first one is stress. Stress is force divided, force means applied force. Force divided by area, that is cross-section area or cross-sectional area. So stress is F divided by A. When it is, since it is linear, to represent that, we can use another word that is called tensile. So if you want, you can use tensile stress. F over A. I'll put a bracket for that. Most of the time that is not. Tensile means linear. Then we have to consider about dimensions. Dimensions of stress. So you write it again. Stress force divided by area. Dimension of force mLT minus 2. Area L squared. Then L is taken up L minus 2. With this L, mL minus 1 T minus 2. Actually, this is the same dimension which is equal to pressure. Pressure is also F over A. So therefore you get the same mLT minus 2 divided by L squared. Then mL minus 1 T minus 2. For MCQs, they might give you such questions. Which of is getting the same dimensions? They might give one answer as one or two or one choice is stress and pressure. Like that. And the second thing, you have to find the of and get it from again right. Force is Newton Nm minus 2. Concern there is a special unit for that. That is what you call that Pascal. When a force of 1 Newton is exerted perpendicularly on a surface having unit area, right? Normally, we can define a new unit. But here SI unit, this is mechanics, I don't want to say actually. SI unit, this is Newton, 1 Newton. This is 1 square meter. And area force must be applied perpendicular to the area. Perpendicular to the area. Then we can say when a force of 1 Newton is exerted on a 1 square meter area perpendicularly, the unit of pressure is defined as Pascal. That is 1 Pascal. So then that is under mechanics. Here, if you want, you can use Pascal also. Remember, scientist names are given normal English name writing method is used. That means first letter is capital, other one is simple. Sometimes in school or some teachers are saying for under first unit, when it is a derived unit, always first letter must be capital, second letter must be simple. That is not the actual idea. That is the name of the person and we are using first letter, two letters or last letter, first three letters, sometimes only first letter. So then that is the reason first letter is capital also. Always we are writing the name, second letter and so on in that particular part of the name in simple. So same theory. Okay, now note down up to this.
Okay.
Okay, now we are coming to next part. That means we did not discuss about the how length increases, how we are going to measure it, right? So that is called strain. Now, strain is the ratio between the increased length, that means extension, and the original length. So that is called so then here we have to write it strain that is extension divided by length. Remember length is original length, initial. Original. So then strain is E over L. I gave all those notations. But remember, there's another thing. Since it is linear, we can say it as tensile strain. That is E over L. But this is not always written. Sometimes in papers they have asked. They normally mention. There's no need to get confused. Tensile means linear. So then after that, we have to consider about dimensions. Dimension of strain. So that is equal to again E over L. E is length, L is a length, times of no dimension. So you know that when there is no dimension, no units. Or when there is no units, no dimension. So therefore directly you can state here, since there is no dimension, there is no units.
Okay, sir.
Always remember the physics, any kind of physics is concerned, any section that involve lot of question related with working out ones. That means questions with numerical values and we have to work it out. So therefore, you have to do more and more questions always any student is concerned. Right. Now, there's another definition. That definition is called modulus of elasticity. That's a small history is there. Initially, it was called modulus of elasticity. But that is common for all three. All three means linearly it extends, area-wise it extends, or volume-wise it extends. There are three. So we can say linear modulus of elasticity, area modulus of elasticity, and other one volume of elasticity. But those are given different names. Linear one, we call it tensile, but tensile word is we are not using here. Again, for that, the modulus of elasticity, when it is linear, is called Young modulus. Then, right? According to the type of the considered object, when it is wire, linearly extends. When a force is applied on an area, the area increases. When a force is given to a volume or three-dimensionally on an object, outwards, even area outwards, the volume increases. In common, we can define one physical quantity called modulus of elasticity. But special names are given for this. When it is linear, we call modulus of elasticity as Young modulus. Young modulus. Here that is also having small differences. That means early it was Young's modulus. But later scientists thought about there is no need to write the process in S here. So then they use Young modulus. But our papers are concerned, we can see both. So then with this, with the apostrophe, or this is with possessive. So he is the person who defined it. Right. Anyhow, Young modulus is denoted by capital Y. Then right. Young modulus is denoted by capital Y. That is on the your right. In common, modulus of elasticity can be defined or can be denoted by capital E. But special one, Young modulus, capital Y. Now I'll come to definition of Young modulus. Young modulus is Young modulus. If you want, you write the first of S. Modulus is stress over strain. Or if you want, you can say tensile stress, better, tensile strain. Right up to that. This is optional.
Okay, sir.
Now, if you use the equation and symbols, this equation can be written using symbols. Force divided by area E over A, because this is stress, this is strain. So you have to remember this equation. When you finish this section today, that doesn't mean the students can't really do A-level papers. It should be done later after the explanation of theory.
Okay, sir.
Now, small example. A wire length of wire length of 2 meters is suspended on a ceiling and at the bottom end of the wire mass of 5 kg is suspended. Mass of 5 kg is suspended. Number one, no, 5 kg is suspended. Then an extension of 6 millimeter is observed. The radius of the wire is 2 millimeters. Then find number one, tensile stress. Number two, tensile strain. And finally, find the Young modulus of the material of the wire. We don't consider the reduction of the area. Now the question is this. Here, when you are doing a question, remember, formulation of a question is more essential than its solution. That doesn't mean you should not get the solutions. Why we said it was not told by me, it was told by Einstein. Because the method what you are using should be taken by the given data and using the known theory. Simply, it is very simple. Here, everything is given. First, they are asking find the tensile stress. So, stress is concerned. If you want, you write tensile. Force divided by area. Force. Can you find force? Yes, it's given. How? Force is given as 5 kilogram weight. That means F is equal to mg. 5 into 10, 50 newtons. So that is given. Area. Area is not given, but we can find area. Since to find the area, cross-sectional area, we have to use pi r squared. So then pi r squared is concerned, we can find A as area is pi r squared 22 divided by 7 into radius 2 millimeters. Everything should be in SI units. So therefore, R is given as 2 millimeters. So you have to convert into SI units. SI unit is 2 meters, 2 into 10 to the power minus 3 meters. Millicentimeter, then minus 3. So therefore, 2 into 10 to the power minus 3 square. This is basic simplification. So then 22 divided by 7 into 2 to the power 2 is 4. Then the power of here is 1. So 1 into 2 is 2 to the power 2. You can write if you want that has 2 to the power 2 like that. But here minus 3 into 2, 10 to the power minus 6. From this you can simplify and get it. There is no need to get the answer directly. Just keep it, but always write the units. Then the other one is force. Force I found it. Again I write it there. Force is 50 Newton. Then you have to apply or substitute the values. So then here you can get it as now stress is 50 divided by F divided by A. A is 22 divided by 7, 4, 10 to the power minus 6. Normally in physics, one thing is there. Remember, when you are doing a question, that means A-level question, in the marking scheme, definite places are there where you get the marks. If any equation is involved for the equation, unless they give it. If they give the equation, they don't give marks for that. Normally, mark is given. Marks are given, we'll say. Then the second one, correct substitution. For that, you are given another 1 mark or 2 marks. But remember this one. Same thing is to be done over and over for another part. They are not giving marks like that. Here, for a correct substitution is this one. You are getting marks. Such a question again comes, that time you don't get the marks again for that situation. After that, remember, for the final answer, with the units, you get the marks. Normally, most of the time, chemistry papers like that, it is separated into the value separately, units separately. But here it's not like most of the time. Both are correct, we give particular mark. 1 or maybe 2. Even it is not divided into split marks. That means for this 1 mark, for that unit 1 mark, like that. Always remember those 3 steps. Correct equation, right? Second one, it should be correct equation. Correct substitution. Then the other one is correct answer with the units. Correct answer with the units. Then you get the mark. Then there's another thing I had to explain. The units. There is in physics, there is no need to substitute the units with the values. Because some unknowns are there, it's confusing. Right? I have seen some places they have done like that. Chemistry, it is an essential thing. They say when you are doing gases like that. But here there is not. But instead of that, you write the units for these. Here A, then square meters. Then after that, force, Newton. We have already shown that. There is no need to substitute that because we have the final answer you get it. Quickly do up to this.
Okay, sir.
Now we want to get the value for strain. So strain is the second part, no? Strain is equal to extension divided by original length. Now extension is how much I gave you extension? 2 centimeters. Correct?
6 millimeters. sir.
Extension in the question I said 2 centimeters. But extension 2 centimeters should be changed to 2 into 10 to the power minus 2 meters. That is E.
The extension is 6 millimeters.
6 millimeters I did. Okay, sorry. So E is 6 millimeters. Then 6 into 10 to the power minus 3 meters. So then initial length is 2 meters. So therefore, this is 6 into 10 to the power minus 3 divided by 2. But here you have written the units, therefore you don't want to write. Only two things are there, even you write it is not a matter, it won't be affecting the question. But anyhow, this is 3 into 10 to the power minus 3, then no units. Both are meters, then no units for that. After that, Young modulus. Young modulus. That is equal to stress, or you can write tensile stress, divided by strain, tensile strain. So now we got the stress. Have you, if you have taken the value, just write the value. Otherwise, here you could have written this as 50 divided by 22 into 4 into 10 to the power minus 6 into 7, like that. You could have simplified also, but it's better to keep like this. So therefore, without simplifying you are keeping, then you write 22 divided by 7. After that, 4 into 10 to the power minus 6 divided by strain 3 into 10 to the power minus 3. See, I will simplify somewhere here. Then what happened is, or here also I can use. Then look at this. So Young modulus, that is y. Y is equal to now 50 divided by 22. Then into 4 into 10 to the power minus 6 into 7. Again divided by 3 into 10 to the power minus 3. Then simplifying is concerned, such situation, it's easy. You can divide it by 2, 11, 25. Then you are getting 25 into 7 divided by 11 into 4 into 3. These two are taken up. 10 to the power positive values, 10 to the power 6 into 10 to the power 3. Then you can simplify this part. At the exam, you feel that you have to do. Most of the time, at the exam, you are getting divisible ones, but not directly. Sometimes it is divided by 13. You can identify later when you are doing past papers. I'll show you. Most of the time, you don't want to use tables. That means logs will say 25 into 7 divided by 44 into 3. Like that you simplify, and 10 to the power 9. Then you have to get the answer. You can use either tables, log tables. About this, I will tell you later. This is equal to 1.326 roughly. 326. into 10 to the power 9 Pascal or Newton per square meter. In log tables, you know that we can find only for all together 4 digits. No? So therefore, one whole number is there, another 3 is enough, the digits. Whole number is 2, another 2 decimal points enough. In anywhere, if they say kilogram force, kgf, that means Newton. That means 5 kgf means you are converting into 50. Remember, kilogram force is newtons.
Okay, sir.
Right. Now I'll give you certain values for Young modulus. Normally, that is not to be mentioned or remembered like that because they give always with the question. So therefore, no need to check those things that much. Anyhow, you write the Young modulus of, don't say that, Young modulus of different materials are having different values. Draw two columns. First column heading, second column heading. Quickly note it down. So just like two columns. Here you write material. Here you write Young modulus or Young's modulus. In common, unit is given in Newton per square meter. So therefore you can write at the top of the column. First one, I'll give only the needed ones. First one is aluminium. The value is 7 into 10 to the power 7 into 10 to the power 10. copper 1.2 into 10 to the power 11. Iron, IRON, 1.9 into 10 to the power 11. Steel, 2 into 10 to the power 11. Rubber, RUBBER, 1 into 10 to the power 6. So those are the basic ones I gave. Another simple question. A wire of 2 meters is suspended from a ceiling and a force of 40 Newton is applied vertically down. The diameter of the wire is 4 millimeters. Number 1, find the extension of the wire. Number 2, one is enough, extension of the wire. So directly what you do is, now we want to find the extension. We know the equation. That is Young modulus. After that you write. The wire is steel and Young modulus is 2 into 10 to the power 11. As a general note, you remember for metals, except for few, metals, Young modulus in the power of 11 or 10 to the power 11. Scientifically written means the value is to be written with scientifically. That means within the first 2 digits, decimal point should be there. In that way, when it is written, 11 is normally the power. But aluminium, it is 10. Right? So you have to remember that for some MCQs. Sometimes we call it the order of the Young modulus for metals is 10 to the power 11. Or even 11 is said, that is also okay. But better to say 10 to the power 11. Now, this question is concerned, we want to find extension. So extension is related with this equation. Y is equal to F over A, E over L. Then check whether the given data, Y given, force given, initial length given, area, diameter is given. So therefore, remaining one is this, we can find it easily. There are 2 methods. One is you rearrange this equation. That means Y cross multiplication E over L is equal to F over A. When you have experience, you write directly. So then E is equal to FL over AY. That is C. Now, what we do not know directly is area. So A is equal to pi r squared. R is equal to diameter by 2. So here 22. So then R is equal to 4 millimeters divided by 2, 2 millimeters. That means 2 into 10 to the power 3 meters. So 22 divided by 7, 2 into 10 to the power minus 3, whole thing square. That is area, and use the units, m squared now. After that, you just write force. Force is given as 40 newtons, and Young modulus is given, L is 2 meters, and Young modulus is still 2 into 10 to the power 11 Newton per square meter. That's after that, you get the equation. There is no need to write it here. Again, if you want directly, FL over AY. So force is 40, length is 2, A is 22 divided by 7. If you want, you could have, you can simplify and keep 4 into 10 to the power minus 6, then 22 divided by 7, 4 into 10 to the power minus 6, then Young modulus. So Young modulus is 2 into 10 to the power 11. Come up to that, simplify, get the answer, give the extension in meters. It comes in meters. These are just to apply the theory only. These are not A-level direct questions. Next class, most of the next section, I'm doing the hard questions.
Okay, sir.
Right. Now, the fundamental graphs. Here normally you get fundamental graphs also for this under this section. Then write heading graphs related to Young modulus. Graphs related to Young modulus. Number 1, extension versus load. Extension versus load. Extension versus load. That means y-axis extension, here load. Load means applied force. Force. Here you get extension. Those are sketches like that. Normally, it's like this. Initially, with the weight or the force load, the extension is proportional up to certain. After that, it increases in a curved method. That means it increases like that. After that, it comes to a certain value, then reduces and increases, and it comes back also. Here, there's a most of the classes they stop here, but that can come backwards. Then normally you think how it happens with the no, actually you can drop to this. Here, when it is breaking, area reduces. That time load is less needed. This is expected part. Actually, up to this. So you have to draw. This is understood now? This is a load. This is proportional. Proportional limit up to this. First you draw like that limit. This is LIMIT limit. Draw up to that. This up to this point straight line. After that I'll explain the regions. Right. Now I change the next one. Load or force versus extension. Force or load versus extension. There what happened is same diagram, but remember it was, we had certain angle here, alpha will say. Now alpha should come. You should not draw like that. I will explain and erase. Now alpha should be from here. So therefore it comes up to this. This alpha is from the other side now because we changed the. After that, this suddenly goes up and changes here, right? And going like this. And it breaks. Actually, here it breaks. Here also it breaks, early one. So then it breaks. Now the diagram is new one, this one, not the blue one. Then next one, stress versus strain graph. Stress versus strain graph.
Excuse me, sir.
Here stress, here strain. That graph is normally, it goes like that as straight line, Remember, up to this straight line. Then slight change is there, slanted. After that, there is a curve slightly downwards, but it does not. So here, up to here, straight line, like that, then it goes like this. After that, it again turns and increases. It turns and increases. And again coming down up to 7. Here it breaks. It means the wire, or better way, wire breaks. And we have to consider certain points there. I will show you those. We'll consider this as up to this A. Here L. Now this is just like this. These are here maximum like that. That point also we have to label, right? That is B. That is B. After that, here maximum value is D. And you can mark the AB. No, C. AB. This is C. Here D. Now, this is a straight line. This is the origin O. First draw it. Up to A, it's a straight line. Now, O to A, that is called proportional limit. Now you write it, not on the graph. OA, proportional limit. Proportional limit. O to L, elastic limit. O to L, elastic limit. Then I'll explain what it is. O to A, force stress is from O to A. Proportional limit is, that means stress. Stress is directly proportional to, sorry, strain. Strain is directly proportional to stress. I want to write directly, but it is therefore stress is directly proportional to strain also. We can write like that. That means force is directly proportional to, no, later I will say. Here it says F over A is directly proportional to E over A. So then F over A, we can make it an equation from this. You have to write a constant to avoid the proportional limit, the sign. So then E over L. Actually, This is K is equal to F over A divided by E over L, what we did, but K is called or denoted by Y later, Young modulus. From there also we can find Young modulus equation. Note down after this.
Okay, sir.
Right. Now, this is a different thing. Now, we have to consider O to L. That was called elastic limit. Elastic limit means when a force is applied, stress comes, strain is there, and we come up to this point and we release the force. We take off the force given. Then the wire comes to its original length. That particular up to this point, therefore we call it elastic limit. But if it exceeds this point up to B or after L, when the force is taken off, that means we remove the force. It does not come back to the original length. It's always greater than the original length. But it's shorter than the final length. Got it? Then right?
Excuse me, sir.
Sure.
Can you repeat what you said now? Because of signal issues, I couldn't hear properly.
Okay. Then here, this is what happened. When a force is given to this, it comes up to this and straight line. So therefore, I said it proportional limit. Proportional limit, directly proportional story comes from A to A, strain is directly proportional to here stress. But you can change it. Stress is directly proportional to strain. Then I wrote after this, you should write here, but I didn't have, you can't see this part. So therefore I wrote there. And F over A is directly proportional to E over L. So F over A is equal to K E over L. So this K is a constant. Actually, that is the Young modulus. The Young modulus is equal to stress over strain story can be obtained from this also. And I send up to a straight line, but L there's a slight turn towards the x-axis. But if you applied force, now force increases, no? That is the reason stress increases. Force increases, we come to A, then after that we come up to L, and we release the force. That means take off the force. When it's taken out, what happens is, again, the wire length comes to the original length. Now it is coming back to the original length again. That happens only up to L. Why it comes to that? It up to that elasticity works. Elasticity means, now only I am saying, increases the length and come back to the original length after the force is removed. That particular situation or that phenomenon, we can't say phenomenon directly, that situation is called elasticity. So most of the elastic material are concerned when the force is removed, it comes to original position. I'll explain those things further. Now, therefore, up to L it is called elastic limit. Elastic limit. Right after that.
Okay, sir.
Now, next one. Now we'll consider B. Then the stress is more, that means force is given further. When the force is given further, stress increases and the strain increases. Strain increases means which increases? Extension also increases up to certain value and then reduces. Then there is no particular method of increase in the length. So up to this, there is a particular way of increasing. This is therefore, after that, it changes its habits or the how it changes. The maximum point is called yield point, YIEA. Then right, when the force is given further, or when the force is increased further, the extension increases. That means when stress is increased, strain increases and comes to a maximum value in the first segment, first part. After that, it reduces. The maximum value at B is there. And after that, the shape changes. Therefore, the change in point B is called yield point. That is called yield point. Then right after that point, the strain increases. That means extension increases, but not in a particular method, but it reaches to maximum value at C. Maximum value at C. That is called maximum stress. Maximum stress. Oh, yeah, sorry. Maximum strain. Strain, we got it there. Maximum strain. And when you draw the line here, this is the maximum stress. Here it is maximum stress. But normally, nowadays we are doing with this one, stress and strain. Almost the stress and strain is concerned. This is the graph you are getting. Then you can write all those. O to L is called another name, elastic formation. Elastic formation. L to C or until the end, that is called, that means normally B to C is called plastic formation. when it is stress and strain, remember stress and strain, normally you get this graph. That means directly stress is proportional to strain. This is maximum stress. Then this is the maximum stress, this graph. Stress, this is maximum strain. Maximum strain. If you plug strain, this graph is related to stress versus strain. Why? Once I told it as strain the other way. This is stress versus strain.
Okay, sir.
Now, even proportion is there, you change that. Now you got it up to B, normally L, we say elastic formation. After that, it does not come back to the origin length. After that, B to C is called here D. There you write the wire breaks. Here, remember, this is stress versus strain, not strain versus S. Now I'll draw the other one because once I told in the other way. So here, now I'm changing the axis. If you change the axis, the previous one comes. What do you mean by that? But normally they are asking stress versus strain. Here it comes like that, coming down, again going up to certain one, then changes like that. This is then strain versus stress. If you have any problem, I'll tell it again because one particular time I said in the other way. First one, stress versus strain. Then you get straight line. After a slight straight line, A. Then B. After that, it changes slightly. Then it goes up. Slightly changes, goes up to maximum. B, after that, it changes without any particular way. So therefore, here it is called right. Now, this is stress, this is strain. Stress is proportional to strain. This is the correct way. But if it is strain versus stress, it is in the other way. Here, this is the yield point. This is the maximum stress. Maximum stress, max stress. Here, this is maximum strain up to this point. Don't get confused with that. I corrected in stress versus strain. This is the graph. Strain versus stress, this line graph. But yield point, all the things are the same. Deformation also you can understand. Plastic deformation, no particular way. Normally, according to this, we use and categorize the materials. We call some material plastic. When we consider those one, it goes up to particular point and stops. It breaks. Those things, last lessons, I will explain because those are not that much needed for the A levels. Those needed ones I do first. That's my method. Slightly needed one, last class, I'll explain everything. Otherwise, what happens is when you are going through these notes, wanted, 100% needed, 10%, 5% needed, all the things are you are trying to get into the brain at the beginning. No, normally get the needed ones, do the questions. After that, near the exam, if you want, you can avoid even the last parts. Once in 10 years' time, one MCQ might come. Like that, it happens. Those things you can understand later. Okay, now I considered, then I'm going to tell you about what happens when the wire extends. When the wire extends from here up to this value, this is the extension. Extension. Now, extension is that I said the wire area changes, but for new A levels or even last syllabus, it was not there. But if you consider this is A1 and this is L1 and new one is A2 cross section and L2. L2 is greater than L1. A1 is then greater than A2. It reduces. In other words, diameter of the first one is greater than diameter of the second situation. Radius of the first one is greater than radius of the second situation. All those are correct. For MCQ set they ask, you can get the answer by considering like that. But directly, different theory is not there. There is one that is called Poisson's ratio related with the radius or diameter. So that is not there in the syllabus. But some MCQs, we are using volume does not change. Volume of the wire, I stated it earlier, does not change. Does not change. So therefore, we can say, therefore, volume of the first situation, L1, A1. I consider this as a cylinder, cross-sectional area of the height of the cylinder. Cross-section of the wire into length is equal to second one, L2, A2. This can be used by you for MCQs. Certain MCQs you have to use that, not down.
Okay, sir.
Right. Now energy. We consider about the energy. Here, the wire extends. Wire extends. This is the extension, large one is shown by me. This is E. This is origin length. A does not change normally. That's our theory. Previous situation I said it changes and take for some MCQs. So here that is force. And now we plot a graph now. That graph will consider now again force versus extension graph. Force versus extension. This is force. This is extension. The graph became, or it was like this, and slight changes and so on. I did not use there. So up to proportional limit, but we can consider up to elastic limit also. Understood? That limit we can consider. Then we consider about the energy. So how to find the energy? Here F is 0. Then average force. Average force. Initial force, then plus final force divided by 2. 0 plus F divided by 2. F by 2. That means half F. Average force. Got it? Half F. Then work done. Here average force travels a distance of E. Then work done. Work done is equal to average force into displacement. This. So then half F into E. Half Fe. Work done is half Fe. That means work done is equal to half into force into extension. Word equation. This is F into E. Better say Fe. Right, note down. This one don't draw. I will explain that. These two and this.
Okay, sir.
Right. Now, this equation you have to remember. Normally, the equations what we are writing better to take into one paper and keep. Right? A4 sheet, you take one and write the equation and define the terms. I will tell about that also. Right. Work done is always in mechanics. Work done stored as energy. Or to do a work, we require energy. We consider there is no loss. Therefore, this is assumption. And we consider work done is equal to energy or energy is equal to work done. Then right? Work done is equal to the energy. Therefore, this work done is stored in the wire. This work done is stored in the wire as energy. using the above equation, we can find the energy. Or some students, teachers directly write energy, but that is not directly. We have to say work done, that is storing as energy in the wire. Right. Now I'll come to this diagram. FE1. So up to this proportional limit. And we'll consider work done from the initial stage up to that situation, extension force. Then here E is 0, F is 0. Normally, practically, we can consider. No force is given to the wire, just suspended. Now, third point will say that find the value is F. Extension is E. This is F. If you want, you can say E1, F1 like that. Now, according to the previous theory, work done is equal to half force into extension. Now consider the graph and up to the point A is, I'll get a different P. Up to P, this area, that area, we'll say A. Then what happened? Area is concerned, area of the graph, area under the graph. Under means downwards. Or we can say same thing, the area between the graph means straight line, and the x-axis. That is equal to area. So area is equal to half is a triangle, base into height. Read 8 or 9. So base is, this is O, this is Q, this point. That is half OQ into height, QP. That means half OQ is equal to E. This is equal to F. That means half FE. Area. Therefore, area between the graph or the line and x-axis or area under the graph is equal to work done. Work done means that is equal to work done or energy stored in the wire. Then write when we consider the area under the graph, that means the area between the graph and the x-axis. Within brackets you write extension axis is equal to half of the product of Therefore, the energy stored in a wire, in other words, work done when a wire extends due to a force, is equal to the area between the graph and the x-axis. Draw, write this part, then upper part. This is the first part, then second.
Okay, sir.
Right. Now you understood, no? Area under the graph means particular point. Now, but mathematically, if you consider this rectangle, from this diagonal, it divides into equal parts. So therefore, even you consider the area between the graph and the force axis, both areas are the same. Then right, according to mathematics, O, Q, P, A, P will label it as R here. One of the diagonal area above the diagonal and below the diagonal having the same value. That means energy can be obtained, energy stored can be obtained even by considering the area between the graph and y-axis. But it is not the direct definition. Mathematically we can prove. Next one, energy stored in, next heading, energy stored in unit length of a wire. When wire is given a force. The wire is concerned a straight line like this. I said it's a just like a cylinder. Area is A, length is L. Then volume of the wire. Volume of the wire is A into L. Volume of the wire A into L. Cross-sectional area into length of the wire. Energy stored, extension is there now, force is here. Energy stored. Energy stored in the whole wire WHOLD, whole wire. That is equal to half into F into E. Energy, that means length L, energy stored in unit length of the wire. Now unit length of the wire, that is equal to total energy stored divided by volume of the wire. That is equal to total energy stored is half F into E divided by volume AL. A into E over L. Half. So then F over A is stress or tensile stress. E over L strain. So therefore, energy stored in unit length of the wire is equal to half stress into strain. That is for unit length. Note down.
Okay, sir.
Right. Now, the same thing, energy further. Now the diagram is, we considered force into extension, force, extension, and it was a straight line like that. We considered two places. Here F1, here F2, related extension E1, related extension E2. Now, average force. Initial force, F initial plus F final divided by 2. F1 plus F2 divided by 2. Then in work done, average force into displacement. Here remember, displacement is E2 minus E1. New length is here, extension, this is the extension. So during this force, it has increased by E1, E2. So now I'll label the diagram. So this is equal to F1 plus F2 divided by 2 into E2 minus E1. That means half F1 plus F2 into E2 minus E1. If I label this as P, Q, R, and S. Then look at this. F1, this is equal to half F1. F1 is PS. PS plus QR into E2 minus E1 is PQ. Since, but PQRS is a trapezium. So therefore, area is given by the equation, above equation. Understood now? So therefore, when a force is given or increased by a particular value to another value, the area between the curve related to the two forces curve and the x-axis is the work done. Now understood, no? Not down. This area only cannot be this.
Okay, sir.
Yes. Today part 1 of Elasticity is over. Normally there is another video for the second one. And special questions are normally discussed in my classes. That's all for it.
Thank you, sir.